In the previous video, you saw how we found the coefficient C sub n. And now what we want to do is we want to look at this theorem. And this theorem says that if f has a power series representation, so if we can expand any function f of x as a power series, then f of x is equal to sigma as n goes from 0 to infinity of c sub n, x minus a to the nth power, where c sub n is equal to the nth derivative of f with respect to, or evaluated at a, and then over n factorial. So I can say that f of x is equal to sigma as n goes from 0 to infinity of the nth derivative of f evaluated at a over n factorial times x minus a to the nth power. Again, this is for x minus a in absolute value less than r. We can expand f of x, and we can say that f of x is equal to f of a over 0 factorial, which is 1, so there's no need for us to write that 0 factorial. And then the idea is that you have x minus a to the 0 power, which again, it's 1, so there's no need for us to write that down, plus f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial x minus a squared plus, I'll write it down here, plus f triple prime of a over 3 factorial x minus a to the third power, and then the idea will continue. Whenever you write it in the form of f of x is equal to sigma as n goes from 0 to infinity, the nth derivative of f evaluated at a, then that is called the Taylor series of the function f at a. So let's write that down. This is the Taylor series of the function f. So this is the Taylor series of the function f centered at a. So we'll put it at a. And again, we say centered at a. Or another thing that you can say is about a. And that represents the same thing. If we let a be equal to 0, then this is a special case of the Taylor series. Then this is a special case called Maclaurin series. So the Maclaurin series is nothing other than f of x equal to sigma as n goes from 0 to infinity. The nth derivative, instead of a, we say 0 over n factorial x minus 0 to the nth power. Okay? There is no need for us to write x minus 0 to the nth power. We can just write it down as x to the nth power. So we have x to the nth power. And if we were to expand this Maclaurin series, again, it's a special case of the Taylor series, we can say that f of x is equal to f of 0 plus f prime of 0 over 1 factorial times n, x. And then we're going to have plus f double prime at 0 over 2 factorial x squared. Plus, we'll do one more, f triple prime at 0 over 3 factorial x to the third power, and then the idea will continue. So again, what we call it a Maclaurin series when a is equal to 0. And we call it a Taylor series when your series is centered at A. So the Maclaurin series is, we can say, centered at A, but A is equal to 0. What I would like for us to do in this video is look at an example and see where that takes us. What we're going to do is we're going to find the Maclaurin series for the following function. So find the Maclaurin series for f of x, where f of x is equal to the natural log of 1 plus x. Okay. So remember, if we are going to be finding the Maclaurin series for this function, we're going to be looking for the first derivative, the second derivative, and so forth, okay? And then after we do that, we are also going to find the radius and interval of convergence. So let's put also find radius and interval of convergence. All right, so one more time. Let's begin from scratch. Remember, we can let f of x be equal to sigma as n goes from 0 to infinity of c sub n, x minus a to the nth power for x minus a less than r. But because we are looking at a Maclaurin series, a is going to be equal to 0 for this Maclaurin series. And then also remember that c sub n is equal to the nth derivative evaluated at a over n factorial. So then we can say that f of x is equal to sigma as n goes from 0 to infinity, the nth derivative evaluated at 0 over n factorial times x to the nth power. And this will be for absolute value of x less than r. So the first thing we are going to do is evaluate, or let's find f of x, and then evaluate that f of x at 0. So we know that f of x is given. F of x is equal to the natural log of 1 plus x. And when you evaluate it at 0, you have ln of 1, which is 0. Let's look at f prime of x. And that's going to be 1 over 1 plus x. And f prime at 0 is equal to 1. The second derivative of x is going to be equal to negative 1 over 1 plus x to the second power. And the reason why that is, let me bring this down. We can write f prime of x as 1 plus x to the negative 1 power. So when we take the derivative, we have negative 1. 1 plus x to the negative 2, which then you can write like this. So we can say, and this is the second derivative, so we can say that f double prime at 0 is going to be equal to negative 1. What I'm going to do is I'm going to go back and keep the notation of the derivatives in this form. That would be easier for us to continue finding the derivatives. Our third derivative is going to be equal to negative 1 times negative 2 times 1 plus x to the negative 3. And we can say that f triple prime at 0 is going to be equal to positive 2. Let's look at the fourth derivative. And we can say that that is negative 1, negative 2, negative 3, 1 plus x to the negative 4. And we can say that our fourth derivative evaluated at 0 is going to be a negative 1 times 2 times 3. Okay. I'm going to do just one more and see where that takes us. So we can say the fifth derivative is going to be a negative 1, negative 2, negative 3, negative 4, 1 plus x to the negative 5 power. And then our derivative evaluated at 0 is going to be equal to a positive 1 times 2 times 3 times 4. So if you were to continue, we can say that the nth derivative of x is going to be equal to negative 1, negative 2, negative 3, all the way to, let's say, negative n plus 1 plus x to the negative n power. Let's go back and make sure that that is correct. So if we are looking at the first derivative, the first derivative, let me go back here. This is the same thing, our first derivative, and this is our second derivative. Our first derivative is going to be first derivative, negative 1. Second derivative, negative 2. Third derivative, negative 3. Fourth derivative, negative 4. So the nth derivative will be negative n. Okay. And then one more time, if we're looking at the second derivative, we are going to have negative 1. The third derivative will be negative 1, negative 2. I'm just going to focus on the numbers. If you're looking at the fourth, it goes up to 3. If you're looking at the fifth derivative, it goes up to 4. So if you're looking at the nth derivative, it's going to go up until one number less. So we say negative n plus 1. And you can check that. Negative 5 plus 1 is negative 4. Negative 4 plus 1 is negative 3. Negative 3 plus 1 is negative 2. Negative 2 plus 1 gives us 1. We'll talk about these f of x and f prime of x as you have them here. Okay. All right, so let's continue with the nth derivative evaluated at 0. So we are going to have, it's either going to be positive or negative. We can see that we have alternating. But the idea here is that you're going to go from, let me get rid of this. I'll come back to the negative 1 in a second. We're going to have 1 times 2 times 3 times all the way to negative n plus 1. Okay. All right. So let's look at this. Our first, in terms of the signs, our first derivative is positive. Second derivative is negative. Third derivative is positive. Fourth derivative is negative. Fifth derivative will be positive. So let's look at this. When your n is even, you're going to have a negative coefficient. So if we're looking for n to be even and a negative coefficient, then we're going to have n plus 1. So now let's go check. If you have the first derivative, when n is equal to 1, 1 plus 1 is 2. Negative 1 to the second power gives you a positive coefficient. When n is 2, 2 plus 1 is 3. Negative 1 to the third power gives you a negative coefficient. When n is 3, 3 plus 1 is 4. Negative 1 to the fourth power gives us a positive coefficient. Okay. So we have a couple of derivatives. We have our nth derivative. And then now what we want to do is we want to try to plug it back into our f of x. So I want to remind you that f of x is equal to sigma as n goes from 0 to infinity. The nth derivative evaluated at 0 over n factorial. And then we have x to the nth power. And then this is for x in absolute value less than r. If we were to expand this, we are going to have f of 0 plus f prime of 0 over 1 factorial x plus f double prime at 0 over 2 factorial x to the second plus f triple prime at 0 over 3 factorial x to the third. We did 4, so plus the fourth derivative at 0 over 4 factorial x to the fourth, and then let me just do the fifth. Actually, I'll just stop here. We just said that f of 0 was 0. Okay. So this right here is going to be 0 plus f prime at 0 is 1. So we're going to have 1 over 1 factorial times x plus the second derivative is going to be a negative 1. So we're going to put a negative 1 over 2 factorial x to the second. Let me go back. So that was our second derivative is negative 1. Our third derivative is going to have, I'm going to put it as, let me put this as, we know it's alternating, right? So we're going to put this as negative 1 to the what power? Here we have n is 0. Here we have n is 1. So if we're looking for the first one to be positive, we're going to do n plus 1 to the first power, and n is 1. Here we're going to have 2 plus 1, negative 1 to the 2 plus 1 over 2 factorial x squared. So this will be n is 2. We're going to do n is 3. By the way, I'm doing a lot of work because this is the first example we see this, where we see this together. But eventually, as I move on, I'm going to be showing fewer steps. Okay. When n is equal to 3, we're going to have negative 1 to the 3 plus 1 times 2 times 1 over 3 factorial. So this is this. And then we're going to do one more. When n is equal to 4, we have negative 1 to the 4 plus 1, 3 times 2 times 1 over 4 factorial x to the 4th, and then the idea continues. So what can we say about f of x? F of x is going to be equal to, I'm going to expand a little bit more. And I'm going to say that this is 0 plus negative 1 to the 1 plus 1 over 1 times x plus negative 1 to the 2 plus 1 over 2 times x to the second power plus, all right, negative 1 to the 3 plus 1 over 3 times x to the third power plus negative 1 to the 4 plus 1 times x to the 4th over 4. And I'll tell you why that is. 3 factorial is really 3 times 2 times 1. So the 2 will simplify and you're left with 3 in your denominator. 4 factorial will be 4 times 3 times 2 times 1. The 3 and the 2 will simplify and you're left with 4 in the denominator. So if you were to continue this, you would have negative 1 to the 5 plus 1, x to the 5th power over 5 plus, and then the idea continues. So we can say, remember, f of x is equal to the natural log of 1 plus x. And right now we are saying that f of x is equal to sigma as n goes from 1 to infinity. There's no need for me to include 0. I'm going to start it at 1 because it's going to be this expansion. So as n goes from 1 to infinity of negative 1 to the n plus 1 over n times x to the nth power. So we can say that the Maclaurin series expansion for this natural log function is equal to this. So sigma as n goes from 1 to infinity, negative 1 to the n plus 1 over n, x to the n. And remember, this is convergent for absolute value of x less than r. This right here is that Maclaurin series. I'm going to call it the Maclaurin series expansion if we decide to expand it. Now what we want to do is we want to find the radius of convergence and the interval of convergence. So how do we find the radius of convergence? Well, why don't we use the ratio test and see where that takes us? Let's take the limit as n approaches infinity of a sub n plus 1 over a sub n, which is equal to the limit as n approaches infinity of, in absolute value, I don't have to worry about the negative 1 to the n plus 1. So let's just say we have x to the n plus 1 over n plus 1 times n over x to the n. So this is going to be equal to the limit as n is approaching infinity of x times n over n plus 1, which we can write as the absolute value of x times the limit as n approaches infinity of n over n plus 1. And by the ratio test, we know that this series is convergent when that limit is less than 1. So we can say that the Maclaurin series is convergent for absolute value of x less than 1. That tells us that the radius of convergence is equal to 1. So the radius of convergence is equal to 1. Because this is centered at 0, we can say that the interval of convergence is going to be from negative 1 to 1. Because remember, if you solve this inequality, you have x between 1 and negative 1. But what should we do now? We should look for the endpoints, right? Always check your endpoints when you're talking about the interval of convergence. So if x is equal to, let's say, negative 1 first. If x is equal to negative 1, then you have sigma as n goes from 1 to infinity, negative 1 to the n plus 1 times negative 1 to the n over n. So this right here is equal to sigma as n goes from 1 to infinity. When your bases are the same, we can keep the base and add the exponent. So this is 2n plus 1 over n, which is nothing other than sigma as n goes from 1 to infinity. Negative 1 to the 2n plus 1 is really equal to negative 1 to the 2n times negative 1, which is equal to negative 1, because this right here will always be positive. So you have negative 1 over n, which is negative sigma as it goes from 1 to infinity of 1 over n. And what do you know about this particular series? This series is divergent by harmonic series, or the P series test. So when x is equal to negative 1, that series will diverge. Let's see what happens when x is equal to positive 1. If x is equal to positive 1, you're going to have sigma as n goes from, so we have sigma as n goes from 1 to infinity, we're going to have negative 1 to the n plus 1 times 1 to the nth power, but you know that that's going to be 1 over n. Actually, I'll leave it. So this right here is going to be sigma as n goes from 1 to infinity. Negative 1, this was positive 1. So negative 1 to the n plus 1 over n. And this, you should also recognize it right away. This series here is convergent by alternating series. Why? Because b sub n plus 1 is less than or equal to b sub n for n greater than or equal to 1. And the limit as n approaches infinity of 1 over n is equal to 0. So we can say that the interval of convergence is going to be from negative 1 not included to 1 included. So let me write the conclusion again. We can say that for the function f of x, which is equal to the natural log of 1 plus x, we have a power series representation of sigma as n goes from 1 to infinity of negative 1 to the n plus 1 x to the n over n. And this is for absolute value of x less than 1, where the interval of convergence is negative 1 to 1. And I called it a power series earlier, but we can do better than that. What do we want to call it? Since this series is centered at 0, we say that that series is a Maclaurin series. All right, this is a lot of information, so I'm going to stop here.